this video we're going to talk about solubility and solubility rules. So this is a reminder from previous things that we've talked about, but when ionic compounds dissolve in water, they dissociate into their respective ions. So, for example, when we take this ionic compound, and we're assuming it's dissolving in water here, the positive and negative ions get ripped apart from one another, and we say that the ionic compound dissociates. So, when ionic compounds dissolve in water, we say that they dissociate. They split up into their respective ions, and that's what happens with compounds like sodium chloride that do readily dissolve in water. But other ionic compounds, silver chloride is one example, dissolve barely at all in water at room temperature. And so compounds like sodium chloride that dissolve easily in a solvent are said to be soluble. Those like silver chloride that don't dissolve very much at all are said to be insoluble. Now, the degree of solubility depends on temperature. For most ionic compounds, when we increase the temperature, the amount of that compound that can dissolve in that solvent increases, but that's not true for all ionic compounds. There are many that the solubility actually decreases as we increase the temperature. I do think an important thing to point out, however, is that even though when we say a compound is insoluble, that means it doesn't dissolve very much, but it does dissolve to a very small extent. Now, it's very small, comparable to a compound that we would say is soluble, but if you have a toxic chemical like lead or mercury, even the very small amount that an insoluble compound will dissolve can be a problem. So we have some rules that we can use to predict whether a particular ionic compound is soluble or insoluble. Now, these rules aren't 100% comprehensive. This won't allow us to predict the solubility of any ionic compound, but it will allow us to predict the solubility of many of the compounds that we'll encounter in Chemistry 1211 and 1212. So the way to read these solubility rules is if you're given a compound, you want to find one or both of the ions in the list here on the left, and you really only need to find one. They won't contradict each other. So, for example, if I wanted to know if sodium bromide is soluble, I'm going to want to either find Na plus or Br minus ions in this left-hand side of the table. And so I see right here, right, Na plus ions, if it's in this group, these compounds are generally soluble unless it meets one of these exceptions. And for these ions, there are no exceptions. So I know that sodium bromide would be soluble in water. If our ions are in this list down here, they are generally insoluble unless it meets one of the exceptions. So, for example, if I asked you about iron 3 hydroxide, we would find the hydroxide ion down here, right? It's generally insoluble unless it meets one of these exceptions. So, if a hydroxide is paired with a lithium or sodium or potassium or an ammonium, it would be soluble, but iron is not one of the exceptions. So iron 3 hydroxide would be insoluble. If we just one more example, if I asked you about sodium carbonate, right? The carbonate ions are generally insoluble, but sodium ions are one of the exceptions. So carbonates are generally insoluble unless it's paired with sodium, which would allow us to predict that it's soluble, right? But because both of these ions are in the table, right, if we go to sodium, it tells us the same thing. Sodium compounds are generally soluble, and there are no exceptions. So either using the carbonate with the exceptions or using the sodium, we would predict that sodium carbonate is soluble. So let's look at a couple more examples. So we have potassium hydroxide, right? So we have KOH, and that has K plus and OH minus ions. And so I want to find, I don't have to find both of the ions. I can find one or the other. I either find K plus or OH minus, right? K plus, compounds containing those ions are generally soluble. There are no exceptions. So potassium hydroxide, I would say, is soluble. And I guess I should mention this now, on tests and quizzes where you need to make these types of predictions, you'll be given this table. So you don't have to have this table memorized, you just have to know how to use it. Alright, for silver bromide, silver ions we know are going to be +1, bromide ions are -1, so that compound is AgBr, so we have Ag plus and Br minus ions. Right, and when I look at my list of ions, I don't see Ag plus on here, and that's fine, we only need to find one of them. Right, we do have bromide ions, and so ionic compounds containing bromide are generally soluble, but when I look at the exceptions, I can see silver is one of the exceptions. So bromide compounds are generally soluble unless they contain silver, and so silver bromide we would predict to be insoluble. Alright, if we go to the next one, calcium chloride. Calcium we know is +2, chloride is -1. So that's CaCl2, we have Ca2 plus and Cl minus. Again, I don't see calcium in here, so I'll look for chloride, and I do have chloride, so chloride compounds are generally soluble. Calcium is not one of the exceptions, so then calcium chloride we would predict to be soluble. Alright, we have magnesium sulfide. It's MgS, magnesium +2, sulfur -2. I don't see magnesium in my list, but I do have sulfide. Sulfide compounds are generally insoluble. And I check, magnesium is not one of the exceptions, so magnesium sulfide should be insoluble. Finally, I have lead-2 sulfate. Sulfate is -2, so lead-2 sulfate is PbSO4. I have Pb2 plus, SO4 2 minus. Lead-2 is not on my list, but sulfate is. And so sulfate compounds are generally soluble, but lead is one of the exceptions. So that means that lead-2 sulfate we predict to be insoluble. All right, one last slide. So we said that ionic compounds, when they dissolve in water, they dissociate. We want to be able to represent that as a chemical equation. And we want to know how many of each ions are produced when it does dissolve. So I want to write the equations for each of these compounds when they dissolve in water. And so calcium chloride, when it's not dissolved in water at room temperature, would be a solid, as with pretty much all ionic compounds. When it dissolves in water, it will split up into calcium ions, and then Cl2 is not a polyatomic ion, so I wouldn't keep the Cl2 together. It's going to break up into 2 chloride ions. So that would be +2 Cl minus. Because it's dissolved in water, we'll give them the states aqueous. Right, same thing for magnesium nitrate. An ionic compound not dissolved in water is going to be a solid at room temperature. Right, that'll break up into 1 magnesium ion. Let's rewrite that 2 plus. And then it'll break up into 2 nitrate ions. Sodium phosphate. Now I have 3 sodium ions. And 1 phosphate ion. So we keep the polyatomic ions together, but if there's more than 1 polyatomic ion, we need to indicate that. The monatomic ions will break apart because they're not polyatomic ions.